Hey everybody, welcome back. In this video, this is going to be a pretty quick one here. We're going to talk about graphs of arithmetic sequences, and I just have one example for you. I wanted to do it, and I think I have one housekeeping item too. That's something we just have to get out of the way. So let me go into our notes. We're still working on 1-2 notes. They're long. All right, so one thing I left out a minute ago and I was talking about, on the last video, I talked about the tabular form. And I guess what should have been said was, first determine whether the sequence is arithmetic. Unless it states it, if they tell you explicitly that it's an arithmetic sequence, then this step is not necessary. But you're going to find that sometimes they want you to determine what type of sequence it is. All right, so first thing you want to check is that n goes up in increments of 1. 1, 2, 3, 4, 5. It doesn't have to start at 1, but if it goes in increments of 1, that's what you want to see. All right, we're testing for arithmetic here. That means it has to have a common difference. These are the same distance apart. So 6 minus 2 is 4. 18 minus 6 is not 4. It's not arithmetic. And it is that simple, okay? It fails the test. And we'll talk about what kind it is in the next section. So that is not arithmetic. All right, that was my housekeeping item. All right, let's get down here to what we're really here to talk about. It says sketch graphs of arithmetic sequences. That's a skill we want to have. But I'm doing it a little bit reverse here. I have a graph, and we're going to explain how this thing comes to be. And it is what it is. All right, and I got this online, so that's why you see it says math bits down there. It says an arithmetic sequence is a discrete function whose domain is a set of natural numbers. All right, now we're going to talk about the discrete pieces highlighted there in just a minute. Okay, but first I want to talk about this function in general that we're looking at here. Now, we need to complete this part where it says f of n, but all I'm given is a set of dots on a graph. Now, if you look at the dots, n is 1, we get 10. N is 2, we get 15. N is 3, no, n is 3, we get 20, and so on. And you can see that this is a linear progression. That is a really linear line, right? If we connected the dots, which we can't do, and we'll talk about that too. First, I want to show you how to write a function for this sequence. And you can see that you're going up in increments of 1, and you're going 10, 15, 20, 25, 30. So, let me clear this out. All right, so pretty much, we're going to write our sequence like normal. We saw that it was going 10, 15, 20, 25, etc., right? And we know that f of 1 is 10. Oops, messed up there a little bit. D is 5, 15 minus 10. And so we quickly come up with f of n is 10 plus 5 times n minus 1. 10 plus, I'm going to distribute here, 5n minus 5. So our final little function here is 5n. And it's looking like it's plus 5. All right, let's keep that in mind here. I want to come over here and talk about that little function for a minute and look at the graph. As a matter of fact, I'm going to go ahead and, oh, not there. Darn it. Maybe there's already an equation here. I'll just finish it. Yeah, good. So we're going to put in 5n plus 5. All right. So here's what I want to talk about now. So that's how you would take one from a graph and write a function. Or you could take a function, put it in as 1, get your number back out, 10, right? And so on, and plot these points. All right, so here's the point I want to make with discrete function talk here. All right, remember when you did y equals mx plus b? You had a y equals mx plus b. And that's sort of the close cousin of this function. I'm going to put that in there temporarily. I don't know if I'll leave it for the notes or not, but that's a lot like 5x plus 5. They're so much alike. Or using our new notation, let's use f of x. Or function notation, right? That makes it look a lot like it. There's a difference here, though, guys. This is a continuous function. When you used to graph these, remember you would say all you need is 2 points, and then you plot them and connect the dots. There's your line. Well, this is a function of real numbers. In other words, you could put in 0.5 and calculate it. There is no such thing as 0.5 with this function. Because remember, he comes from the sequence. N is, well, let me go back up here and edit. What I'm trying to make a point of here is there's nothing in between these numbers. N is 1, N is 2, N is 3, N is 4. It doesn't have anything in between. In other words, the first term, there is no such thing as the 1.5th term or the 1.25th terms. There's just 1, 2, 3. That's why they call it discrete. It's not continuous. So we would say here, this guy is a continuous function. There's numbers in between that I can plug in for x. This is a function of all real numbers. This is a function of natural numbers only. So when you plot the graph of a sequence, it's a linear function. It is, but it's not the same. So it's just a series of discrete points or dots, right? This is what they call a discrete function, and this is a continuous function. And I'll fill that in on the notes. Okay, I said this video was going to be short. I'll see you in recursive sequences. Thanks for watching.